section of this morning, and now Kurt will continue with his mini course about the rigidity and the partial rigidity.
Okay. I'm excited to conclude this mini course. Today, I want to wrap up a proof of the theorem that I started proving last time. And then I want to spend the last bit of the course talking about some non-rigidity phenomena and partial rigidity phenomena that I think are interesting. So let's just remember what we were doing. We were looking at the setting of totally partial hyperbolic actions, and I said there was a secret theorem that we were proving, which is this one. For the experts, you can replace this SLDR with any higher rank semi-simple Lie group, but if you have an action of sort of a big enough Lie group, semi-simple, and you need three things, right? First, you need to preserve the volume. Second, you need this total partially hyperbolic condition. This is what we spend most of the first lecture trying to figure out what this means. And lastly, you need accessibility. In the abelian setting, this higher rank semi-simple Lie group gives you the measurable solution to the derivative cocycle that I was asking for and the super accessibility property that I was asking for. So that's the abelian theorem that we were trying to prove. From these assumptions, you get that it's actually an extremely restrictive action, right? That it has to be some translation action on a biquotient space and not just a quotient space. And we looked at the example of geodesic flow on hyperbolic 3 space, or more generally, hyperbolic n space within at least 3, to see that you really have to have this compact group K appearing in the factor sometimes. And we went through 3 key steps last time. We upgraded the measurable continuous metrics that the higher rank property gives you to continuous ones using the invariance principle. We used the metrics in the quote-unquote higher rank trick, moving along the kernels or the hyperplanes corresponding to the totally hyperbolic condition, to build transitive isometry group actions on each leaf. And then the last thing that we spent quite a bit of time discussing was how to build a funny fiber bundle where we expect not only the RK action to act, but also the nilpotent groups to act. So our setup in the last step, this path group step, is the following. We have a group K hat, which is going to act on X. This is the structure group of the fiber bundle. Right? Not only was it a fiber bundle, it's a principal bundle. What else did we have? Well, we showed that the RK actions lifted X hat. This is the lifting lifted action by pushing framings. Right, our bundle was a bundle of frames. And last one, I didn't discuss in detail how to build these actions, but I gave some intuition, right? If you have a framing, you now have a way to say which direction is which inside a coarsely up enough, and you should be able to build a nice nilpotent Lie group action. Now, the important thing that I want to emphasize here is that I'm not actually going to use the isometry group action before. Like, if I am translating on a Heisenberg group, the left translations are not isometries. So somehow I need to dualize the isometry picture and leverage the framings to be able to build these actions which parameterize the manifold. But I'm asking you to take my word for it that this is possible. So these are nilpotent group actions. There's many of them. W lambda leaves. So we build 3 actions, or 3 types of actions, from the data we had before. Now, in the actual setting of the semi-simple Lie groups, these actually are, in the Anosov setting, these are actually coordinates for the Lie group. In the partially hyperbolic setting, these only generate the big Lie group that we want to talk about. Some of these n lambdas will contain the roots of G, so we'll be recovering parts of G when we do this. But we'll also be moving outside of G with these lambdas, right? Because we're really using the full course-Lyapunov and parameterizing the full course-Lyapunov. And we sort of have to move outside of the G orbit unless we're looking at a rather silly action because of the accessibility assumption, right? If I stay within the G orbit, then the whole thing is just a single G orbit, and it's kind of a silly theorem. So there has to be something new that comes out of these actions, comes out of these constructions. So what's the goal? The goal is now to glue these actions together. So glue these actions into a single Lie group action H acting on X hat. If I can do this, because of accessibility, this H action is going to be transitive. And so X's hat is going to be an H homogeneous space. And then I can just re-quotient out by K hat, which is now part of the structure, the homogeneous space structure of X hat, and get that my original X was a bi-homogeneous space. So this is the plan. So I'm very vague here. Let me be more clear. I.e., so I want this H action X, and I want all 3 of these groups to embed into H. So I want K hat to embed into H, RK to embed into H, and N lambda to embed into H. And then I want the property that this diagram commutes, whatever that means, right? So that if I embed and then act, it's the same as just taking the original action on X. So there's a tool to do this. So the tool is to use free products. Right, I'm thinking optimistically, right? I assume that I already have this. If I had this, I could just take the free product of these groups. And of course, if I have a homomorphism, if these do embed, then that homomorphism extends to the free product. So why not take the free product and try to build a Lie group factor to which acts? Right, so what do I want to do? I want to take K hat, free product RK, free product, the free product over all lambda in delta of n lambda. I'm going to call this P, because if you think about what this group is doing, it's really an element of this group describes a way to build a path. Right? If I have a point X and an element rho in P, how does rho act on X? Well, you do the obvious thing, right? Rho is a product of elements, G1 star G2 star G3 star Gn. I just start applying, right? This is really a way to build accessibility classes together with these 2 elements, right? If I ignore this, if I look at the action of this group, I'm really building an accessibility class, right? So I just start I need to read from right to left, right? Because I want to act on x. So it's gn minus 1, all the way up to g1, and then I end at y, or rho acting on x. No, maximal compact is bigger. K hat is just the centralizer of the Cartan. Or it's the centralizer really of the SLDR action. So it's difficult to construct one where you have K and an SLDR action. Right, I cheated in my example before when I talked about the geodesic flow, right? Because this isn't really extending to a semi-simple Lie group action. And if anyone's interested, I can describe an example, or you can look in the paper. We have, I think, a 4-page example section, maybe longer, where we really build a lot of examples. But there are examples where you have a bihomogeneous space structure and not just a homogeneous space structure. It's really essential. Okay, any other questions before I continue? All right, so what's going to happen if I think that H is going to be x hat is going to be a H homogeneous space? Well, of course, this is some infinite dimensional group. That's part of the issue, right? Elements of this group, I'm not allowed to combine them because it's a free product. So it turns out to have a very nice topology and a very bad topology, right? The topology is nice in that it's a CW complex. The bad news is that it's an infinite dimensional CW complex, so it's not metrizable. It has a lot of bad properties, but it retains path connectedness, which is the key property that we use later that passes to the factor. So what do we want to do with this free product? I want to look at a stabilizer. And I don't want to take the full stabilizer, but I want to take the connected component of a stabilizer. So again, I'm thinking optimistically. What happens if H acts on x hat? Well, the action should be locally free, right? Because you're quotienting by a discrete group. So of course the action isn't free, but it's locally free, and the local stabilizer of a point is just trivial. So if I look at the kernel of the map that I get from P to H, that should just be the stabilizer of a point. Right? It should, the kernel, which is this funny normal subgroup, assuming we've won, turns out to be a nice normal subgroup, which is the stabilizer of a point. And this is sort of the key proposition. If the stabilizer in P of x connected component of the identity, right? So I don't look at all stabilizers, I look at some stabilizers, as a normal subgroup of P, then P factors through a Lie group action in the way that I describe over there. Why? Because when I quotient by this normal subgroup, I'm going to basically be homeomorphic to the image, or at least locally. So I'm going to have to be homeomorphic to a manifold. So the quotient group is going to be forced to be a Lie group. Even though I haven't mentioned smoothness at all, Lie groups do have unique smooth structures for which the left and right multiplication is smooth. So as long as I can get this, sort of smoothness, a smooth structure sort of pops out. I don't know what coincides with my original one yet, but I know that a smooth structure pops out, which is nice. Well, how would you prove this? Well, it comes down to asking what is the stabilizer? for the P action of a point X connected component, this is the set of contractible cycles. Why? Because let's look at how I define my action here. If rho acts on a point and it stabilizes it, then this had to be just coming back to where I am. And if it's connected to the identity, right, I have to be able to contract this path back. So it has to be contractible, right? I have to be in the identity component of the stabilizer. So I have to be able to bring it back to the identity using a continuous deformation. Right? So and it turns out, because I have transitivity, that the normality of this subgroup is equivalent to this cycle group not changing as I move my base point around. So this is the last step. Proposition, the stabilizer in P of X, connecting component, is a normal subgroup of P, if and only if the stabilizer in P for every X and Y. Right? Why? Because what does it mean to be normal? It means that I want to take a conjugation, right? So I take a point X, I move out to Y by a path, I go around the loop, and then I come back by the same path. I want that to close up again, right? So because I sort of know that I come out to X and back to Y by the path here, this property holds. Mm-hmm.
So is this stabilizer there still a CW subcomplex or something like that?
In the end, it will be. It would be nice to know that in general, but I don't know how to prove that in general for a smooth action, say.
But it's path connected.
Sorry?
Since they are contractible, it is path connected.
It is path connected, exactly, by definition. This isn't really the way that we write it in the paper. We don't look at the full stabilizer. We build up enough elements of the stabilizer to claim this, but this is morally the way that the proof goes, or should be thought about. Okay, so how hard could this be, right? Well, it turns out to be a little bit tricky to show that this stabilizer doesn't change. And in fact, for many actions, you have actions, whenever you have actions parameterizing the courses, you're going to have the structure. But the sort of cycle group at a point is going to change. If you think about even just say the space of contact flows on on-off contact throws on 3 manifolds, you can parameterize the stable and unstable leaves. And this stable cycle group is related to this temporal function. So if the temporal functions coincide everywhere, are the same at every point, that means that the stabilizer group is the same at every point. And this is another way to prove, under the assumption that the temporal functions are the same everywhere, that you have a homogeneous structure. Okay. So how to prove this? So to show constant cycle structure, what do we need to do? We find enough cycles. To generate let me say enough cycles in common to generate this stabilizer at every point. And there are two types of cycles. So one is a type of cycle which we call symplectic cycles. So this is what happens when you take actions of n lambda and n minus lambda. Right, so this is the analogous of rank 1 cycles. And this is somehow symplectic pairs are usually the enemy. They're the obstacle in higher rank. And in this picture, surprisingly, they're your friends, right? This is the easy case. Why? Because if I take a cycle that's using only lambda and minus lambda, lambda minus lambda, lambda minus lambda, lambda, and I come back, and then I apply an element of kernel lambda, well, notice that by definition, of the lift, I'm just pushing the frames forward. So before we had this annoying rotation appear, but when we passed the lift, we've gotten rid of the rotation. So this is really just a homothety. And because I took it in the kernel of lambda, this just commutes. RK commutes with the kernel of the corresponding exponent, commutes with the n lambda action. So this is just the exact same cycle over here. In particular, the space of cycles in n lambda is constant on n lambda orbits, or kernel lambda orbits. And because of superaccessibility, kernel lambda is ergodic. So it's constant. It varies continuously. This is just not varying. You have the constant cycle structure everywhere. A very nice little trick. The hard one are the so-called geometric commutators. Yeah, exactly. So these are constant by kernel lambda transitivity. So I'm not going to say anything about these. I'm just going to draw a picture. But what do? I take two exponents, lambda and chi. I don't want to move along minus lambda and minus chi, but I just want to invert the elements that I move by. These are really Lie group actions. So if I get to here, I went U, then V, I can go U inverse, V inverse. And I can ask, what do I need to complete this? Well, it turns out you can prove a lot of structure about the thing that you need to complete this commutator when chi and lambda are not proportional, right? I've already dealt with the case when they're negatively proportional. If they're positively proportional, they're the same group. So I already know the relations between the same group and a free product. I just need to understand the relations between these different ones. So this is the hardest, well, one of the harder parts of the paper. To handle these, you basically need to show that this quantity, which we call rho of u v x, if it starts at x, it would suffice to show that it was constant, but we actually show that this is some polynomial. This takes a constant polynomial form. The arguments are tricky, but tricky and technical, so I want to not go into this. Sorry? Yeah, so yes, Desheng is right that here I'm really abusing notation here when I say this. Rho is really an element of this free product, and if you give me two Lyapunov exponents, chi, we actually know that this completion has to take place in between basically the cone generated by lambda and chi, all positive linear combinations of chi. So if there are, say, I take two adjacent weights, this doesn't appear, that they have to commute. What you should be thinking about is the commutator of this matrix, which is one of the elements for the Weyl chamber flow on SL3R. And this matrix, E13, E23, let me switch these, sorry. E12 and E23 is E13, if I do this computation. So we basically reconstructing these relations inside of a semi-simple E group or one of its representations by purely dynamical arguments. Okay. I don't want to say much else about rigidity. I just want to give some historical comments. I realize that maybe I was a bit too light on contextualizing this theorem. So for G actions, there was a lot of development in the 80s by people like Margulis and Zimmer, who basically showed superrigidity theorems for homomorphisms and cocycles, respectively. Right, this is how we get that first step, that we can solve the derivative cocycle measurably. And the crucial tool here, the common crucial tool, was the action of the diagonal subgroup. Which are, in more broad terms, called Cartan subgroups. Right, so I look at how these diagonal ones act, and they turn out to dictate a lot of how the Lie group acts. Later, late 80s, sort of the people started to notice that the diagonal was sort of the driving force and asked, well, what sort of things can you get just from the diagonal action? Or what sort of, right, these semi-simple E groups are related to symmetric spaces. So Ballman and then Burns and Spatzier showed geometric rigidity. For higher rank manifolds. And these are manifolds with large dimensional flats at every point. And if you think about, if you have a RK action, right, the flats, a flat in a manifold looks a lot like a copy of RK. So can you push this even further? This was done in the 90s. By Katak and Spatzier. So 90s. Dynamical rigidity. Not for G actions, but for RK. So in particular, you have Katak-Spatzier. I'm just giving the highlights here. I'm not giving all of the people and other names in between. But Katak-Spatzer showed local rigidity for homogeneous on Nossoff RK actions. Or ZL actions. K plus L at least 2. And let me just add irreducible, right? I want no factors whatsoever, even though the real condition is no rank 1 factors. And this led them to sort of a wide belief that, right, sort of irreducibility of the action plus some Nossoff element or some hyperbolicity should force some homogeneity. And I want to show you that that's not quite true. So that's the last part of the mini course, which is non-rigidity. And I want to start with an example that is irreducible. And in fact, several people have probably seen before, even though you didn't realize you were looking at an R2 action. So I'm going to start with an example we looked at before, which is just a product of Nossoff flows. So I want to take R2 acting on X cross Y. Alpha is the product of an Nossoff flow phi T and an Nossoff flow phi S. And what do I want to do? Well, I want to sort of destroy the factor structure. And in my first attempt, I'm just going to destroy one of the factors. Let's destroy the vertical factor, right? The ability to project onto Y and have the flow descend. So how can I destroy this factor? Well, I do the following thing. I want to define beta of Ts acting on a point x comma y is, in the first factor, I do the same thing, psi t of x. But in the second factor, I don't just want to do phi s of y, right? That would just be reconstructing alpha. I want to add a cocycle here, sigma of t comma x of y. And sigma from r cross x to r is a C infinity cocycle such that, so first, the integral of sigma of t comma x d Lebesgue, if I evaluate this at x, I want it to have 0 average for every t. I can certainly arrange that. But I also want it to be not trivial. So 2 sigma is not a coboundary. Which, by Lifshitz, because everything's an Nossoff here, just means that the integral of sigma of tx d mu of x is not equal to 0 for some mu. Right, it's 0 for Lebesgue, but it's not 0 for some other measure. Well, what's happened? Well, I can't project onto the vertical coordinate anymore, right? I mean, I can, but I don't know how to act on y without knowing what x is. So the ability to project and project the flow has disappeared. And in fact, if you just take s equals 0, and the horizontal line, letting t vary, this is a skew product where I have an Nossoff flow on the base and an Nossoff flow on the fiber with 0 average. So what are the Anosov elements? Let's compare them. Here I have alpha, and here I have beta. I have my axes here. I have my axes here. For alpha, it's basically everything. The only thing I can't do is move along the kernels. And the kernels are just the axes. Right, so the red is Anosov. And these are non-Anosov. These are, in fact, even non-ergodic. They're very singular degenerate elements. Well, what happens over here? Here things get a little bit more complicated. Here, I still have the vertical line letting S vary. This is still an isonosov flow and has a well-defined kernel, right? So the kernel is the horizontal line. Right? So this is still non-ergodic. But what happens to sorry. This is this is T. This is still the kernel of the fiber exponent, right? So this is the kernel of the fiber exponent. So in particular, there's no way that these elements can be Anosov. I want horizontal to be T. I thought I had figured this out, and I always get confused when I do this. The vertical axis, T is 0. Oh, yeah, you're right. The vertical axis is where T is 0. Okay. So this is a well-defined kernel, right? If I just move by S, I'm not doing anything in the base. But now, what does it mean for an element to be uniformly expanding? Let's think about it. Well, I need sort of, at every periodic orbit, expansion to occur. First of all, this is a perturbation if sigma is small. So I can guarantee some Anosov elements. But if the integral of sigma, let me put it this way. I want to look at the function consider for every A in R2, the integral of sigma of A1 comma x, d mu of x, where this range is overall measures mu. If this is always, say, positive, what does that mean? Yeah, if this is always positive, when I move horizontally, right, I'm trying to expand or contract Sorry, I'm getting confused here. I'm trying to find Anosov elements, right? And basically, I'm trying to think about what happens when I'm very close to this horizontal line. Previously, in the direct product case, if I was very close to the horizontal line, I would have strong expansion here and very weak expansion here. But now, sigma can be a bummer, right? Sigma can sort of cancel out the, yeah. I want this to be bigger than A2. Okay, now I got it. So this is a condition that I need, or minus A2, sorry. Minus A2 plus A2 to be bigger than 0. Right, if this is true for every invariant measure, then when I move horizontally, I'm going to see uniform expansion. A is A1 comma A2. T comma S, I guess, to be consistent. I claim that this is if and only if T comma S is uniformly expanding. Horizontal. For every mu. All right, this is certainly necessary, and I claim it's sufficient, right, by Lifshitz. So what does this mean? Well, I look at the supremum of these, and this defines the equation of a line. So there's some line I have to be above to be an Nosov. And the same thing is true on the opposite direction. Right, there's this cone that I've removed from the set of Anosov elements. So this cone here, these are non-uniformly hyperbolic elements. But somewhere in that cone, one of the measures is negative, or this sum is negative, so things go down. That's not different enough, is it? Oof. I'll do a different shape instead. So this is the set of Anosov elements. The reason that I said you may have seen this example before is exactly this horizontal action, right? I've chosen sigma to have integral 0. That means that the Lyapunov exponents for the Lebesgue measure, this still preserves Lebesgue measure, aren't going to change, right? So this is the kernel of chi Lebesgue. It's now ergodic, and in fact, it's Rudolph's example of something that's K and not Bernoulli. So this is K, a K system, which every element on this line that's not the origin is K, but not Bernoulli. This was Rudolph's example, which was inspired by Galikov, who did it for the same construction for shifts. This is why I want integral 0. Everything else will be fine. Whatever this integral is, this integral is going to determine the kernel of this measure. So moving along that line is going to be a K but not Bernoulli system. Okay. Let me add one more remark. Two more remarks. One remark and two questions related to this. I want to make some more remarks about K, but not Bernoulli, and then I need to go into opening up both cones simultaneously. Yeah. So remark. So every C infinity example of K non-Bernoulli systems are done through smooth skew products, are elements of partially hyperbolic Z cross R or R2 actions. Right, either you have a torus space or you have something like this. Technically, I'm lying here because you can put sort of a non-uniformly hyperbolic base. You can put, say, the Katok slowdown, which is not uniformly hyperbolic, but non-uniformly hyperbolic. But morally, all examples are constructed this way. So the question is, if f from x to x is C infinity volume preserving and K, but not Bernoulli, does ZR F modulo F contain a copy of R? Right, so is there a non-trivial flow for which the system is not an iterate of that flow? So far, all our examples are this. I would be surprised if this were true, but it would be nice to know that it's not true. It's just a nice pattern. The related sort of secret question beyond that this motivates, motivates this easier one, is if f from x to x is C infinity volume preserving K non-Bernoulli and uniformly partially hyperbolic, a lot of assumptions, can f also be accessible? In every example we have, because it's a skew product, you have a base which is hyperbolic, you access the fibers by only accessing the orbits of the flows. So these always end up being what's called essentially accessible, which means that the stable, unstable accessibility classes sort of are saturated by the fibers upstairs, the orbits upstairs. So answering the first question would probably also be an answer to the second question. ZR, so this is the CR centralizer. Even the measurable centralizer would be interesting. We expect high complexity systems to have lots of things commuting with them, right? Bernoulli shifts have crazy things that commute with them. But K systems are not Bernoulli systems. So is it possible to have a K system which has trivial measurable centralizer? That's an interesting question. But even C0 centralizer, you can ask that. That would be the sort of strongest, no, weakest. You can let R vary and ask the question in a variety of regularities.
The question is not imply that it's a smooth skew product, right?
No, it does not, and that's what I'm going to get into with this last discussion. All right, let me give myself some more space. Because I wanted to find a new action. I probably won't go through the details of how to construct it. But the upshot is that I can do this to both cones at the same time. So there exist genuine R2 time changes. Right? I can think of a skew product as a time change of the R2 action because I'm just reparameterizing the orbits. So when I say a genuine R2 time change, there exists genuine action, which is an action with the same orbits reparameterized. Of product actions such that for every Course-Lyapunov foliation W, the contracting elements for that Course-Lyapunov foliation are properly contained in a hyperplane. So what happens, let's call this action gamma. What happens for the action of gamma? I still have the same picture of not changing the axes. These are still going to be the kernels of the Lyapunov exponents for volume. This time change is still going to preserve a volume. I'm still going to have this same picture, but now I'm going to do it to both axes at the same time. Sorry, half space. Thank you. I wrote one thing and meant another. Right, so these really are no longer the full half space that we get for totally in Asaf. We see this picture that we talked about in the first lecture of we get a cone of an Asaf elements, but not a half space. And then the Anosov elements is everything else. So what Amy was complaining to me about before is that I didn't say how this threw a wrench into a lot of conjectures. In particular, it was thought, in particular, I should say first that this Weyl chamber picture implies that gamma has no factors. Why? If I have a factor, so if pi, maybe it doesn't factor onto x cross y, it factors onto something else, is a dynamical factor. Such that R2 factors through a flow. Well, there would be some way that associates the element R2 here to what element the flow was here, right? So this means that there's some sigma from R2 to R. Such that if I look at an element A acting on a point P and I project it down, this is the flow. I need a new flow, eta, sigma of A, pi of P. Right? This is what we mean by a dynamical factor. That there could, of course, be R2 factors, but I sort of can't reduce it and reduce the dimension of the acting group. Well, this would mean that kernel sigma sort of has to freeze a Course-Lyapunov. Because I can't send all the Course-Lyapunovs down to Z. I can only send some of them. But I have to send something, right? So whichever coarse Lyapunov gets sent down to Z, if I apply something in the kernel of sigma, well, I'm just moving in the fiber. Things are sort of moving parallel to one another all the time. These cones have to collapse whenever I have a projection. And that's exactly what we see in this cube product example, right? The cone that we opened up, I can't project onto that Lyapunov exponent. But the cone that I left closed, I can project along that direction. So because I've opened up both of the hyperplanes into cones, I can't factor onto anything anymore. So this action is irreducible in sort of the former conjecture. So the context here, it was widely believed that irreducible Anosov higher rank actions, and when I say Anosov, I just mean there's some Anosov element, right? So one of these cones exists. Were all homogeneous. This was sort of inspired by Katak and Spatzer's local rigidity result, which I erased probably a while ago now, which says that if I start from something homogeneous and irreducible and I perturb it, I have to come back to homogeneous, as long as that system is irreducible. And if I start from something reducible, well, the irreducibility seems to be the key, right? It's true for homogeneous systems. But the key thing that was missing is that reducibility is not stable, right? So I can start from something reducible and build an irreducible guy through this construction. There is some hope. So note, these are all through time changes. So we can still ask the question, is every irreducible R2 action Anosov R2 action either a time change of a product or homogeneous. And there's some evidence to suggest this. First, and this is maybe the weaker piece of evidence, this is the only way that we know how to do construct other examples, right? So once we figured everything out, we declare we figured everything out and conjecture that that's everything. Maybe this is the naive way to do things. So this is the weaker piece of evidence. What's the stronger piece of evidence? The stronger piece of evidence is the other theorem that I haven't really discussed, that this big theorem was sort of partially inspired by, right? This team got together because Damjanovic and Zhu proved something about upgrading conformal structures and being able to get nice geometric structures on higher dimensional manifolds. And Ralph and I had proved a setting in the context of abelian actions, not G actions, where you assume totally Anosov. You assume that these clones all collapse. And if you assume totally Anosov in one-dimensional coarse Lyapunov foliations, then you do have this picture, right? You can't do this funny time change to destroy things. You must be homogeneous. So this is true when totally Anosov. So evidence for yes is true for totally Anosov and one-dimensional courses. And this is my theorem with. Okay, I'm out of time. Thanks.
Okay.
Question, can you consider product R4 action on SL3R squared and do the same example?
No. So what do we need to do to construct these examples? We needed to have a cocycle to shear. So if I take SL4R and do a product there, I don't have a way to build a cocycle, right? The irreducible higher rank guys are cocycle rigid as well.
SL3R squared, so you have R squared times R squared.
Yes, but each of the R squared components is cocycle rigid. I don't have a way to shear one of the R squareds into the other.
So it's only kind of from one dimensional. Okay.
Yeah, it's only for products of rank 1s that you can do this.
Are there any other question?
Okay. Yes. So, yeah, I meant to get to this and just ran out of time. So this is ongoing work with Al Boozman. We have 2 results about Anosov actions. So first I'm just going to write, so VINHAGE Boozman. So first we have higher rank Planck. Which says that Anosov actions are suspensions over their accessibility classes. But things get complicated because you can take a product of an Anosov diffeomorphism and an Anosov flow, suspend the Anosov diffeomorphism, and so I can only sort of suspend one, right? So this is RK. So Plant showed that an Anosov flow is either topologically mixing or a constant time suspension. So we proved the same thing. You have a constant time suspension over something which is topologically mixing. And you suspend part of the action, but not the whole action. And so we introduced this notion of suspension rank. The other thing we're proving is that, so this gamma action, gamma has every non-zero element ergodic. And in fact, every non-zero element K. And the next step after this, expected, based on the relationship between gamma and beta, gamma, the kernel actions, so the Lyapunov kernels are not Bernoulli. So this would sort of be a first step towards getting accessibility, but you don't quite get accessibility, right? Because the accessibility classes of this, if considered as partially hyperbolic elements, are going to be sort of the accessibility classes, the stable and non-stables of one of the former factors plus the full R2 orbits. That's what we're showing. And this is how we deduce K in ergodicity. This is Burns-Wilkinson we're using here. And you still have this property that something commutes with it, right? It's now a question that I erased. So you still have a flow that commutes with this, right? Because I have a transverse direction as part of the R2 action. But it no longer is a skew product, right? So it's we expect it to be K but not Bernoulli, but that would be the next step. Yeah? Yeah, exactly. This is another related question. So if an Anosov action has every element which is K is also Bernoulli, is that action sort of fitting into product or homogeneous? Does it decompose as a product of rank 1s plus a product of homogeneuses? I don't think it'll be possible to have every element Bernoulli. That's another interesting question, because in the product cases, those are not ergodic. I guess for, say, Wald chamber flows or something like this, every element is Bernoulli, right? So this should be some strong irreducibility condition that every element is Bernoulli. That's another great question. If these are not Bernoulli by results of Vogelpiat, Kanagowski, Rodriguez-Hertz, right? We won't have exponential mixing here. So that's another direction to go. If you have an Anosov RK action such that every element is exponentially mixing, can you prove rigidity? And that rules out products as well, right? Because non-ergodic things certainly can't be mixing.
Any other question? Okay, then let's thanks for the mini course.